Yeah, so we can do introductions, just like go down the line. My name's Jeremy. I graduated from Harvard in 2015 and then spent some time building this distributed deep learning library in Spark, which is this like open source big data compute platform. But I actually just left that and then like about to go to training. So feel free to ask me questions. That's actually what you're here. Justin.
Cool. I'm Justin, master student at the U. Working on distributed deep learning and low-power computation.
I'm Matt, freshman at MIT and interested in machine learning.
I'm Jay, sophomore here. I've done computer vision, particularly face-related things. I help run the MIT analysis.
Hey everyone, my name's Anthony. I'm a junior in CS here. Interested in this talk because partnering with the Jay on a final project for a class that's essentially writing a chess AI. So I'm curious to see if there's anything relevant.
Oh, have you seen Matthew Live paper?
Yeah, Matthew Live solved this problem for his thesis, right?
Yeah, 2015.
Yeah.
Like I don't know, his results were like perfect, but yeah, he worked on
Okay.
So I'm Simon, first year physics graduate. I'm just currently looking around looking for my PhD. So just here on universities.
My name is Thomas. I'm a freshman here at MIT, and yeah, I'm really interested in machine learning.
Yeah, me too. I'm also I like natural language processing.
Hey, I'm Tommy. I'm a grad student at the U. I'm working in the space between operating systems and machine learning.
I'm Charles. I'm Charles. I'm a sophomore at BU, and I'm interested in machine learning. And I help run BU's at least.
I'm Jane. I'm a sophomore at BU, and I also help run BU's MIC.
I'm Jason. I'm a grad student in security here.
My name is Luke. I'm Master's Aeroastro at MIT, and I'm doing machine vision, computer vision for television.
I'm Isaac, a freshman at MIT, just doing machine learning at
Hello guys, my name is Andrew. I'm a junior here at MIT majoring in computer science, and I'm very interested in computer vision.
Hi, I'm Vishru. I'm a fifth year physics PhD student, and I'm super interested in computer vision.
Hi, I'm Shani. I'm a freshman here.
I'm Albert. I'm also a freshman at MIT and also just interested in machine learning.
There, I'm a law student at B, interested in machine learning.
Good response. Lots of surprising. I guess that I can jump in. I do want to get a feel for like where people are at with regards to like what I should assume is known and can just cleanly built upon. This is like what I should go into detail on. So this is a high level just like structure of the talk. I guess the motivation mostly looks like why do we care about it, and I guess deep reinforcement learning in general, but specifically like what improvements did DeepMind make to this version of AlphaGo that allows it to basically in 3 days get to the level that AlphaGo lead was at. I guess that's human state of the art extraordinarily quickly before it took them 40 days plus of training in order to get there. And so they made some improvements that made that worthwhile. But I'm going to spend a decent bit of time talking about like sort of components that may or may not be well known. So does like everyone here know what convolution is? Or I guess like yeah, probably sure. Like I'm going to build on top of convolution, so I might like go into a little bit of detail. We can also treat it as a black box. But basically, like going from a straight up convolutional neural network to a residual network, which actually contains convolutional layers, is one of the like major distinctions between this basically like policy and value network and the policy and value network that was used in the original AlphaGo. And so like the details of how that architecture like does a better job of modeling the structure of the images that, well, I guess in this case we're treating the board as an image, but does a better job of treating the board state. Like that's fairly important to its improvement. I'm going to go into differences. So I guess at a high level, these are sort of like 5 major differences, and this like new reinforcement learning algorithm is going to take up a majority of the talk just because it's where a lot of the value as far as improving the speed of training is improving this, as well as improving the smoothness of training is concerned. Basically, self-play is just the step of having basically an agent that has a network that generates a policy, which is the actions that you take given a state of the board in Go. And you talk about Go a little bit. Basically, self-play will be that agent playing against itself, and through basically having slightly different variants of itself play one another, and then basically adjusting the weights to prefer the actions that are taken by the superior network, it'll improve itself across time. There's also supervision in the original version of AlphaGo, and so basically they trained on a ton of human experts, and those human experts created a classifier that allowed it to basically like simulate playing like a strong human. Here they start from scratch. So this is like one of the major differences that we'll talk about in more detail. Certainly, like only the stones are inputs. So I guess we should talk a little bit about Go. So has anyone here played Go, by the way? Okay, cool, wow, okay. So I'm not going to go into tons of detail about the game. I guess there's a high-level notion that you want to capture space, and the way that you capture space or capture territory is by cordoning it off on the board. You can also capture your opponent's pieces, and you capture their pieces by surrounding them. And so you and your opponent will take turns sequentially placing stones in ways that you intend to surround your opponent or to take space, and at the end of the game, you evaluate who has captured more space on the board, and that determines who wins. But frankly, like a lot of the games end up in a state where both players realize that one of the players is going to win, so they resign. Which saves a lot of compute. You can go over that. But basically, in this setup, there are a number of patterns that you'll see in the game, and what the process of teaching someone to play Go looks like is showing them what patterns exist and how to take advantage of those patterns in order to improve. And so they actually hard-coded a lot of those patterns into the input of the original AlphaGo. And here, what's important is that there was no human notions of how to play Go or like what structures are relevant that were hard-coded into the representation that was fed to the network that was deciding what to do. Single ResNet rather than a policy and value net. So basically in deep reinforcement learning, there's this concept of a value network, which basically takes the input state of your environment, your board, and gives you, in this case, the probability that the player who's about to play is going to win. And there's a policy network that tells you, given the state of the board, what action should I take. So basically, all of the points in the board that are not currently covered can be covered by the policy net. And if you have separate networks for both of those, you will end up like overfitting in subtle ways to both of those tasks. Whereas if you have a single network that has two outputs, the ability to predict who's going to win will have like a little bit different information. And so if you give this network that signal, oh, by the way, like this is the player who won given this board state, it'll have more information that informs what action you should take, and vice versa. So if you know what action is optimal based on basically this Monte Carlo tree search that's determined better actions, you know more about who's going most likely to win the game. And so by merging those information, you effectively regularize the network. And so that merge is actually one of the major differences. We talked about simpler tree search. So in the original AlphaGo, there are basically these rollouts to the end of the game, and they're just very quick sort of logistic regression algorithms that output the optimal policy at every single state and have you simulate taking all of those actions very quickly. I guess the tree search here doesn't involve that, so they basically cut it down to purely doing MCTS with networks, and I'll go into detail on that in this sort of new reinforcement learning algorithm explanation. So basically, it incorporates this sort of like look-ahead search inside of the training. So I wanted to talk about foundations here. So certainly, convolutional neural networks are the like foundation of the original AlphaGo, which basically use consonants to represent the board state, which basically leads to a policy as well as the prediction of the value of that position for a player. Residual networks are also very important. I can actually go over that in some detail. So I guess that we can talk about that because that's an important difference. Monte Carlo tree search is the algorithm that does a ton of the work here. So I guess Go as a game is this sequential game where you're placing stones one after the other. And that like basically leads to a root node, which is the current state of the game, and a number of nodes underneath that, which are the next possible step, and a number of nodes underneath those nodes, which are basically going to like map the game out to the very end. And there's obviously a huge number of possible configurations of the board state. Like Demis is famous for saying, oh, it's like more than the number of atoms in the universe. But basically, this tree-like structure is what makes it make sense to use something like Monte Carlo tree search. And so we'll talk about that in some detail. this entire framework is like known as deep reinforcement learning. And here mostly through like policy iteration and policy evaluation. And so this is a particular take on how to use deep learning to inform a reinforcement learning agent. Finally, we'll talk a bit about RL and AlphaGo. So I guess in a lot of ways, the fact that you have this value output and the policy output treats them as auxiliary tasks. This multicolored tree search is going to be triggered at the root node of the tree, but also at the subnodes that maximize a score. And we'll talk about how that score is computed, but basically we're only going to search the parts of the Go space that are likely to have extremely good outcomes for the player who's making the choice. And then the parameters in the network are going to update towards the winner of this sort of self-play matches that are going on. So this is at high levels, like the structure of the talk, and I'll sort of dive into detail on each of these parts. But certainly should be interactive, because I know that like there's like a pretty broad range of knowledge, and people probably have questions, so like you guys should ask questions at this point if you have any. Anyway, silence. Okay. Yeah, I can just.
Do you know
like,
anything about the cons? Do you know about the shape of the cons they used?
Yeah, so I guess that if you think about the import board shape, the board is actually 19 by 19, and there's also this sort of like black or white stone. So like you can have a black stone there, you can have a white stone there, but you can have no stone there. And so you have this 19 by 19 by 3 input, which is a tensor that you run your initial convolutions over. And so basically those convolutions are just going to be this like, I don't know. So in this architecture, it's like 3 by 3 by 3 by 3. So you have the 3 dimensions in like black, white, and none. And then you, over the 19 by 19 board, will slide the convolution over, and that will create a feature map. You'll have many different convolutions, and they'll create many feature maps. And then you'll feed it through a set of layers of those convolutions as you run convolutions over the feature maps that you created. And you will end up with this signal at the end of the network, which is like whether or not that player won, which is the value signal, and what the optimal basically actions were in your policy, and that'll feed back through to the filters. So I don't know if that answers your question, but basically there's this board input representation, and then the filters actually kind of.
Yeah, I guess the question is like, why would they choose such small like cons? That seems kind of small, like 3 by 3 by 3.
Yeah, so I guess that is, you have a deeper net. So I guess like one advantage of the rasa is like you can go to like 100 plus like numbers of layers. And so even if you have small filters, you will end up with like deeper in the network, a representation of a larger part of the receptive field. So like your 3 by 3 filters go over the first layer of the net and create a representation, but then you have 3 by 3 filters that are over those filters. And so they're actually going to look at a much larger receptive field underneath, because they're going to be looking at like a number of filters simultaneously. And I guess that as you get deeper and deeper in the net, you end up with a larger and larger receptive field on the input. And so it actually ends up being like a pretty strong representation of the whole thing.
Has anyone done anything sort of like analogous to the sort of like, you know, gradient descent on parameters to sort of figure out what these representations look like, or kind of like are?
Yeah, so that would actually be really interesting if you were like a Go player who wanted to know, say, like which parts of the board are interesting to the network or are powering a decision as far as the policy is concerned. But I haven't seen tools like that, and I guess like they haven't figured out like releasing the code for AlphaGo, in part because it's tied in with a bunch of like confidential libraries that people put on. Yeah, I don't know that I've seen any of that.
There's some stuff called deconvolutional networks.
Right. Yeah, that's right.
I don't know.
But has anyone done that for, you know,
I don't know.
Yeah, so true. I haven't seen it. But he brings up a good point. So like, deconvolution is basically like mapping your filter like back to the input. It can create really beautiful representations. I guess like there's this paper by Zero and Fergus. They actually won the internet in 2013. But they like show basically images of the representations at different levels of the network, and you can watch it sort of like hierarchically learn the structure of the input data, which in this case was ImageNet. So that's a good point.
Can you talk about how they deal with the edges of the rule? Like, is there something about Go that's conducive to using combats? Like, do they formulate what kind of rules they use at the
edges?
Yeah.
So I guess that it's like a classic padding situation where like you can start your convolutional filter at the like, corner of the 19 by 19 board, but you might miss out on some structure because there's basically like in every single other, so like in all the internal points on the board, you'll have filters like run over it at multiple places, whereas at the edges of the board, will only have one filter on it. And so one thing you can do is pad it and like have like this extended version of the board with zeros on the outside, so that you hit every single point on the board an equal number of times with your filters. That said, I don't know what parameter they use for padding. That said, it's like usually not actually that important. Like people play with it, but they don't like get substantial differences in their scores. That said, if you're doing generation, it can look really weird because at the edges of the image, you'll have this like input that like doesn't actually know how to like bring in other parts of the representation because it's like only hit by like a small part of the receptive field. Anyway, this is like another issue. But yeah, is that it? I guess like you can look up what they do with the padding in the paper, but I'm not sure. Yeah, just like a hyperparameter you would do.
Yeah, so in this case, with Go, they can use convolution because they map the board as an image. But are there any other domains where you can use convolutions, or is it pretty much only when using like input data that kind of looks like an image?
So if you like clarify kind of looks like an image, the answer is like kind of yes. So I guess convolution has a structure to it. It basically, so one way you can think of it is it emphasizes locality. So like the thing that is in the receptive field is all that matters to the feature map, and everything that's not in the receptive field effectively has a weight of 0. And so in images, you have this structure where there are very strong relationships between the pixels that are right next to one another, and there are relatively weaker relationships between the pixels that are like at one part of an image and like a much like farther away part of an image. And so you can actually save huge amounts of computation by assuming that the interrelationships between like pixels that are far away from one another is like very small or like next to 0. And as you get deeper in the network, you'll start to consider those relationships, but only after they've been considered in the context of the relationship of the pixels that they're local to. And so there's this locality assumption that shows up, like say in like graphical machine learning, where like, you know, say it's a social net, like people who you're local to are like much more important than people who you're far away from. And so you should like sort of bring this prior that you only care about local information to the data. And so that's like one valuable aspect of convolution. But another valuable aspect is you get this sort of location invariance. And this is true in Go as well. So I guess on the board, if you have the exact same structure, but it's in a slightly different place on the board, so I guess the board is somewhat symmetrical, and so in this case, what you care about is the symmetry, and it doesn't explicitly capture the symmetry, but it basically doesn't care where like the location is, and it'll still pick up the feature in the same way. And so I guess like the analogy to images is, you know, if you have a ton of faces in a room, for example, you will like drag your like feature locator across, and if it picks up like a particular type of feature, it can find it in different parts of the image. It doesn't have to only find it in like those particular pixels. And so convolution also gives you this invariance to translation, which carries over to Go somewhat. Because like if you have the same orientation of pieces, but like, you know, like shifted over or shifted down, you want to like be able to map those to one another, and so save yourself like a ton of computation time.
So are convolutions used elsewhere other than like images and like Go?
Yeah, so they're used in natural language processing, and like Facebook has a really high quality, very fast, like runtime fast use of convolutions for like machine translation. It's used in audio processing, which has the same sort of like locality structure. Like the things that are close in my sort of stream of words are more relevant to one another, and you also want that translation invariance. Like you don't care where in the audio stream you heard a word, you want to be able to detect what it is. And so they're also state of the art in like a lot of audio processing. Yeah, it's like vision, like some parts of NLP, audio. Certainly any signals processing is like likely to be helpful. So yeah, actually, so the genetic code is like, you know, HCTGs, like the sequences. The sequences have this locality structure to them. So it's like another example where it could work. Yeah, I haven't seen it, but I'm sure, I'm not surprised at all. Like, pretty reasonable.
You can use it across time too. There was this paper at CDPR, temporal convex. So they have like 1D convolutions across time.
Yeah, that's right. That's how all the natural language consonants are set up.
Nice.
And also how all the audio consonants are set up. There's also the video for video, right? So
there's a body of theory to try to like extend them to be like totally general. There's actually been a NIPS like tutorial about this year. And sort of like the body of work is called like graph confidence, because graphs can sort of represent basically any structure. So that is like extend confidence to literally everything.
Yeah, that's right. And graph convolutions are also already state-of-the-art in a lot of graph processing tasks. It's like you like do want to do edge detection or like edge instantiation, like what edges in this graph don't already exist. Yeah, they're like fairly general in terms. As soon as you abstract the types of structure, they'll learn finite convolution. And so in the context of Go, like some of that structure is present, and so you can take advantage of the representation that worked in image processing. Yeah, yeah, we should run. That's fair. So this is the high level structure of the talk. I'm going to jump into specifics on the differences and then go through this RL algorithm in detail. Is there a time you want for stop? Is it 1 hour or something else?
7, I think.
7? Okay. Cool. We can do that. You mean 6?
Sorry, 6.
Yeah.
This is 1 hour max.
Yeah, I assume you meant 6. That's good. Great. Also, those are good questions. Like, that's all. So here are some results that like basically motivate this talk. So this is a comparison between AlphaGo Master, AlphaGo Wii, and AlphaGo Zero. AlphaGo Wii is the one that won the competition. The ELO score is a score that basically takes into account both the strength of the players that a Go player has played against, as well as whether or not they won against them. And so basically like Lisa Bottle had this ELO of like 3,500. And in the Go community, most of they use Don and like the number of Don that you are to represent your score. But they tried to match it onto this rating system, which is like more similar to something that you'd see like in chess or in a lot of competitive like dynamics where you want to figure out where people are against other people. The really impressive thing is getting to the level of AlphaGo Wii in about 3 days. So I guess this AlphaGo Zero was trained on 4 GPUs, and so it's like a relatively small amount of compute, and they very quickly got to an extremely high level. AlphaGo Wii was trained on some 248 GPUs or something like that, and like AlphaGo Master was on 48 GPUs. AlphaGo Master is this algorithm that was released in like about January of this year, and it went 60-0 against some of the best professionals online. So I guess that algorithm basically takes the reinforcement learning architecture that I'll show you here, but also incorporates human training data. So basically they still take like some 35,000 games and initialize AlphaGo Master with the play of, you know, a strong amateur, effectively. And so in playing games between AlphaGo Zero, which has like no human knowledge embedded in initially, and AlphaGo Master, they ended up sort of beating Master like 89-11. So it wasn't completely decisive. Obviously against Wii it was like 100-0 because the differences are dramatic. But basically this will show you the sort of scores of these against one another in terms of ELO. And the raw network there is just the pure policy network, not improved by Monte Carlo tree search. I'll talk to you a little bit about how MCTS actually improves the quality of the policies. But the ELO rating of that is about equivalent to AlphaGo Fan. So initially they like beat European Go player. And this AlphaGo Fan is like the sort of policy, the policy that they use to play that player. Ideally, you know, you would do away with Monte Carlo tree search, but Go does have this sequential structure that's not cleanly captured by a continent. Like you need some sequential algorithm, and you can do a continent through time, but it's not trivial to like replicate that tree search structure. And so this is just how the raw network performs if you just output whatever the policy net says you should do without doing any Monte Carlo tree search. So self-play is the only thing that AlphaGo Zero uses in order to improve. So there are about 30 million positions in the KGS Go server. So that's the server from which they took the data that they trained the original AlphaGo on. And they gave it, you know, tons and tons of expert moves, and actually blew away the state of the art in terms of like predicting expert moves. So prior to the original AlphaGo, the state of the art was about 45%. Where the question is like, can we predict what the expert will play given the state of the board? And they pushed that all the way to 57% when they integrated all of the features that they had sort of hand designed. So, for example, like Go will have the situation where you and your opponent are competing for territory, and you like have this ladder where you play in a sequence over and over again, and end up in an end state that is like really bad for you, and the ability to detect that can be difficult for just a straight up policy net. So they'll like say hard code that, and that'll be one of the features they have. Or like there'll be different situations that I'll sort of show you that end up improving this like feature-based one to 57%, but without the features, they also just get 55.7% accuracy on expert moves. And so that sort of shows you the difference between like with feature engineering and without feature engineering. So just with the board state, they can still do very, very well. And so I mean, like, one way you could think about this is like, oh, well, you know, additional human thought and human features helps, and you can do somewhat well without it, so we shouldn't be that crazily surprised that AlphaGo Zero is capable of, you know, outperforming these other nuts just because, like, we're already fairly close. It's like between, you know, 1.3% off or something like that. And so it initializes AlphaGo, the original one at least, at a strong amateur level, whereas this one's not initialized at all. And I guess one of the struggles with that is, like, reinforcement learning very consistently struggles to get a foothold on whatever game that it's playing. It basically has to do some search, like random exploration through space, and without that initialization, I might just like never find structure in the game that allows it to win systematically and win well. And so a lot of these algorithmic improvements make it possible to go from not having very much information about the game to being able to perform well. And it's like one part of what this is like pretty impressive. So another major distinction is like they didn't do a lot of feature engineering that exists. So we talked a little bit about laddering. So they would feed these ladder features to the network. So this sort of stone color is the like black, white, or none feature that I was describing to you. They have a bias. There's a sort of number of turns since a move has been played, the number of liberties that exist. So like a liberty is a particular type of structure inside of the Go game that you can hard code and that you can say either exists or doesn't exist in a particular position. But basically there are a huge number of features. This is specifically for the networks, that is for the policy network and for the value network. But they also have these sort of like logistic regression like rollouts, and so they have feature engineering for the rollouts and for the tree policy and Monte Carlo tree search. And so they'll sort of show it whether there's sort of in the COD pattern, which is another like setup for a captured stone. There's a diamond pattern, response pattern that they've hard coded. These are basically like features for this like very fast logistic regression rollout that was done in the previous version of AlphaGo that was taken out in this. And so they basically took out all of these features and just trained on the straight up board state for everything.
Can I say something about that?
Yeah,
like I understand what they're. I really understand that like it's a cooler result when you say like we don't need any of this. Like it's just the board, right?
Yeah.
Like, but like if you were just cooking up like the best like network ever, would you also like take like their zero and plug in these features too, or do you think maybe they actually make it work? I don't know. What would you do?
So there's this really important question, and I think that it's like why people care about this. So it's like why you call it important. Whether or not AlphaGo Zero learns importantly different structure around how to play Go than a human. And so one fear is that if you initialize it with the number of features that humans know to be important, then you'll start in this local maxima that incorporates those types of concept and won't be able to efficiently break out of that mode of playing the game. And if you play from scratch, you will end up doing much wider search over the space of possible strategies and possible actions. And so there's this question of like whether AlphaGo Zero is better than AlphaGo Master because it's not looking at human training data is in a way from scratch or from zero, figuring out how to play the game. So it's not obvious to me that it does learn like dramatically importantly different strategies from the ones that humans have. But some indication that it does comes out of the ordering in which you can watch AlphaGo Zero learn different types of structure in Go. And so you can basically watch that it learns this laddering structure very late in training, whereas if you were teaching a human how to play, you would show that to them very, very early. It's like one of the first patterns that you teach some like person who's learning Go. Whereas it would learn more advanced or complex or abstract ideas somewhat early in the training process.
Gotcha.
And so people have been pointing to this fact as an indication that it might be learning what types of like sort of structure, types of strategy that don't actually exist in classic human play, and that maybe AlphaGo Master doesn't even have.
Cool.
And so one thing you could do is have Go players analyze games between Master and Zero and see what happens. But I guess that it's not obvious to me that there's a huge difference. So I guess beating another program like 89 to 11 feels to me like almost a wash. And so yeah, it's not obvious that I can like conclusively say that you're going to get better features if you don't initialize it with something. Certainly bootstrapping is going to be like somewhat faster to some local equilibrium. It's not clear if it'll slow you down and jump into another one, but that's my go about it.
Question, if you do like reach that local equilibrium, what are ways that you might jump out of local equilibrium?
Yeah, so how do you jump out of local equilibrium? So one answer is you enhance exploration, and basically another program will take advantage of or exploit any weaknesses that you have, assuming that it can like find them. And so I guess there's this tau parameter, which basically is going to modify the weight that you put on basically how many times you've tried a state or seen a state action pair in the past. And if you enhance the amount of exploration that you do, you'll do a better job of basically taking advantage of the weaknesses of the local equilibria that you fall into. But in general, it's a pretty big problem where you do insufficient exploration, and then somebody finds a solution that makes it really hard for you to win. So I guess a good example is in Dota 2, like OpenAI created this Dota bot that had a particular condition that it was really poor at, and human players would lose consistently to this bot until they realized that there was a particular strategy that they could consistently do that would beat it, and then they could beat it all the time. And that type of thing happens if you do insufficient exploration over action space when you're doing self-play. That said, more exploration will consume more of your time, and it won't obviously be clear to you whether or not there are solutions that you're not finding that you could be. And so you can enhance exploration dramatically and slow your training down, but it's sort of hard to tell whether or not you're in a local equilibrium or not, unless you have some external source of validation. And I guess that's kind of a problem with the scores that you'll see. So I guess there's this implicit claim that the ELO of AlphaGo Zero is 1,500 above AlphaGo lead, but we don't have a least at all that's at that level, and so it's actually really hard to know since it's just trying to generalize from these fairly low level ELO ranges to higher ranges. It's hard to say whether that generalization is succeeding or failing, and I guess that it might not actually be that good if we had a human who was at that ELO score and you're not actually performing that well, you're just comparing it to yourself. And it might also be overfitting, so it's not clear that AlphaGo Master has an overfit to a particular solution and we're beating it because we have a slightly different solution. I guess that it's really hard to adjudicate as soon as you're past human range. And I guess this is true in almost every machine learning task, right? Because once you get past the ability of humans to label the data accurately, it's really hard to train above that in a way that's consistent. And so self-play is this hope, oh, maybe we can get better, but we can't evaluate whether or not it's doing better than we are after we are no longer capable of making those labels. So I guess that yeah, it's just pretty interesting open question.
Hasn't played a human yet. AlphaGo Zero.
No, so they played Master against 60 humans. They haven't played Zero against humans as far as I know. So yeah, that's a good question. And I think AlphaGo Master won 60 to 0 against the best humans in the world. So it'd be very surprising if it beats AlphaGo Master but loses to humans, but it's not a comprehensive one. So yeah. What was it? And then I would like to go to this guy. Okay, so I'm gonna kill full screen. Yeah. So there are two more major slides. So this sort of single ResNet replacing the velocity and value network slide, as well as this new reinforcement learning algorithm. So the new RL algorithm is a lot about how Monte Carlo tree search works, and how it decides where to move at particular points in time. What heuristics are we using in order to make a decision about where to go in each step of the search tree, and how are we using that to inform our policy network and figure out what actions to take. The single ResNet rather than a policy or value net slide is somewhat straightforward though. So I guess in the original version of AlphaGo, there's a policy net and there's a value net. The value net basically tells you what the probability of the current player winning is, and the policy net tells you what action you should take given a state of the game. So here you see the states as inputs and the value of the policy as outputs. It's sort of inverted. So for AlphaGo Zero, you have a state, and that state will generate both a policy and a value. And so having both of these outputs is useful because they both contain information that's relevant to the other task. And so you can actually use them as regularizations so you guarantee that you don't fit to particularities of the task at hand. There's this little equation which basically is the loss function for AlphaGo Zero. And in this case, we have a sum of squared errors. So the value here is the sort of 1 or 0 for whether or not this player wins the game. And you're just going to compare that to its true value. So if the player actually won, then you give it a good score. If they failed, so I guess this is going to be a number between 0 and 1. This is going to be the actual label. And this will just be part of your loss. And that's in a reasonable range. There's also this cross entropy loss function. So that comes out of the policy net. So you have some log probabilities. These are the probabilities that come out of your policy net. And then you have this pi t. So these are what the true probabilities of each action should be. And since we don't actually have this sort of objective answer for Go, we're going to get a better set of probabilities around what we should do from Monte Carlo tree search. And so this network is going to look to this algorithm that like iteratively looks through the game state and use, in effect, the value network as an approximation of future states of the game, and use that information to create even better probabilities so that it can feed back into its policy net. And I'll talk to you about that in detail in the next slide, but this loss function is basically, did we accurately predict whether or not this player is going to win? Did we accurately predict probabilities on our actions that mimic the probabilities from Monte Carlo tree search? And then finally, there's a weight decay or like regularization term. And so you don't want to overfit. And in general, you can do that by making sure that you don't have like disproportionately large weights. And so this is just like classic L2 regularization.
So is the loss function often because you say it's like that, it feeds back into...
Yeah, so the loss function, because it's self-play, is recursively feeding back into itself. In that as you like improve the value net by making updates to the network as a function of the gradients of this loss function, you will basically use the value net in Monte Carlo tree search to evaluate the subtrees or all of the value of all of the sub-actions of like the potential states of the game. And that will create a set of probabilities for your policy network that are better than your current policy network. So I guess that, I think I showed you in one of the early slides that like your raw policy network is actually substantially worse than your network with Monte Carlo tree search. And so what it's trying to do is take the answers from Monte Carlo tree search and feed that back into the policy network so that it can learn a more optimal set of probabilities for the output. And so in that sense, like as your self-play goes on, it feeds back into itself. Yeah, that's fair. Same thing with this like value score. I guess that you will get better estimating the value that is like given a state, like who's likely to win as you see more and more games. And so that'll also be good. But the label doesn't actually change. It just knows who won or lost.
Can I ask you one more? You have like one you have like V1, V2 for every state in the game?
Yeah, that's right.
You only get one Z at the end?
Yeah, exactly. And that Z is going to be in every single like state action pair. So like you'll have, this is what my state was, here's the action that I took, and here's whether or not I won the game.
So do you do a gradient update on each one of those?
You sample uniformly from a number that you see across time, because there are just way too many to use all of them. Basically, you'll go back over the state action pairs in self-play and take some like proportion of them to serve as gradients for your network. And those labels, are just going to come out of like the actual end state of the game for the value net, and out of Monte Carlo tree search for the set of probabilities for like what your policy net should do. Yeah. So this is the last and like somewhat heavy slide. Basically, this RL algorithm is what enabled the ability to learn from scratch, certainly, but also this sort of like smooth learning trajectory. So basically, MZTS is going to be run at every single like move that you make. So you'll have this like AlphaGo agent that's playing a game, it takes an action. As soon as you've changed the state of the game, it'll run Monte Carlo tree search, which will look at sort of three important factors. So one factor is I'm in some state, like the board is in some state, and the policy network is giving me some prior probabilities on what actions that I should take. So you just run the policy network on the state of the game in order to get those probability outputs. And so that's P, the state and action pair in this case. So basically, you'll have this root node, which is the current state of the game, and every edge leads to a new state of the game, and those edges all correspond to actions that you can take. So basically, all of these edges have this prior probability associated with them, and also have some number of visits. So basically, you'll have this tree that'll constantly be searching the space of options, and it'll consistently go down places with high prior probability and places that have high values determined by the value net. And so you're much more likely to consistently search a route that has lots of potential underneath it that is likely to be played than something that's not likely to be played. And so the number of participants also allows you to sort of point at exploration. So I guess you want to like go away from things that you've seen too many times, and so this will also allow you to heuristically like explore the space of possibilities, taking into account both like how valuable is it, so like what's the value is determined by the value net as well as determined by the policy net, but also like what have we not seen before, so that we can make sure we don't fall into some local equilibria that can be taken advantage of. So this third bit of information that it cares about, the value of the state action pair, comes out of the subtree. So I guess all of these, so I guess you have your root node, you have all of these edges that are potential future states of the game, and then at those future states, there's a subtree behind them of the most valuable states that are underneath it. You can run your value net on those states, and in averaging the value net of the states that are underneath a subnode, get this estimate for the quality of that subnode. And so the value of the state action pair is determined by the mean value of the subtree underneath the node that you've explored. There's an exploration process that depends on the quality of the position. So it's only going to look at the parts of the subtree that pass its standards as far as the number of visits and the prior probability is concerned. And so the search under that subtree is biased towards the things that you would actually do, as opposed to random actions that could happen in that subtree. So basically, these are the three inputs to your decision for whether or not you should explore another node. It's like, what does my policy net say I should do? How many times have I seen it before? What does my value net say the value of the subnodes under that is? And so this just formalizes that. So the simulation starts from this root node and then selects the move. It always selects the maximum move out of Q of S and A. So here, Q is just this mean value of the subtree under the root. QSA is this mean value of the subtree of the node. And then there's this U of S of A. So given a state in action, what does the policy net say that I should do? So that's this sort of prior probability from the policy net. And how many times have I visited that state? So you're going to divide by 1 plus the number of times you've seen that state. And this composite score gives you basically what they call a confidence. And that confidence score is going to determine what am I going to search in Monte Carlo tree search next. So basically, you'll find the one that has the maximum value, and now you have another node that you've selected, and now you're going to be considering edges that come out of that subnode and that subtree. And you can run this continuously to the end of the game, so there are a few end conditions. One is when you resign the game, so if the value net outputs a value that's sufficiently low, you know you've sort of reached the end of the game, and you call that a resignation. There are also literal end states of the game. So I guess once you've passed twice in Go, the game ends. But also once all of the spots on the board have been covered, the game ends. And so once you hit one of these end conditions, you end MCTS. But basically, this simulation will continue until the point at which it gets cut off. And you will basically get some new search probabilities. So basically, you're going to use these three. You're going to continuously search the space. You're going to take an action after you at the end. But you also want to update your policy network and update your value network with what you've learned by traversing the states of the game using MCTS. And the way that you do that is that you take the number of previous visits and realize that the number of times that you visit a state is going to correspond to the value of that state. And that's because inside of this, when you're choosing a path to go down, you're constantly looking at the probability that the policy net outputs as well as the values underneath that subtree. And so when you search the space, you end up consistently going down routes that are valuable and consistently not going down routes that aren't valuable. And so since you're running this many, many, many times, you actually end up with a nice heuristic, which basically lets you update your policy network's labels. So what are the best probabilities with this, and it's sort of cut off, but basically with this normalized version of the number of previous visits to MCTS. So if you want to know what the map looks like, it's just going to say, take the number of previous visits and divide by the sum over the number of visits over all of the states. So it's just like the softmax except for the number of states. And so that will feed back into what we saw on the last slide. So that feeds back into this pi of t. So we're going to look at the average of the number of times that we've seen the state in Monte Carlo tree search to improve our probabilities that will feed back into the policy net through this loss. we're going to look at who actually wins the game once we finish the rollout, and that will tell us basically whether or not we accurately predicted who would win in our value net or not, and that will improve the probabilities that are output by the policy net and probabilities that are output by the value net. And we'll play many, many, many games and continuously improve both of these networks using one another to make decisions. And then there's randomness obviously built into it through certainly a heuristic around the number of times that you visit a state. So I guess like we're dividing by this here, and this gives us basically exploration, as well as this tau parameter. So this tau parameter basically says that I want to like emphasize exploration more or less. And so you can increase the weight that it puts on the number of times that it's seen a state, and that gives you more or less exploration. But that was a lot, so you guys should like jump in with questions. Or you all got it. You can all go code up to AlphaGo Zero. Okay. So, yeah, so it's just like high-level RL and AlphaGo Zero. So basically, the network has this auxiliary task, MCTS has triggered each move, and the parameters update to the winner of the self-match play. So that's the end of the presentation. I don't know if you guys have anything else.
So for the auxiliary task, do they show the network weights up until the last node?
So they share network weights until the last, at which point they branch into the regression output, which is just like your value net with like sum squared loss and policy net. So yes.
And are the gradients weighted in any way?
So there's no weighting on the loss function. That's not an unreasonable thing to do. So like there's this question, I guess he's saying, so you could have like, alpha times the value net's output plus beta times the, policy net's output. And you can say, okay, like this value net is way more important. Let's like have a like large coefficient on it. Yeah, they happen to not do that. I mean, it's normalized. So I guess if you think about it, it's currently like basically evenly weighted in that your like sum of squared errors. So this is going to be 1, and this is going to be a probability between 0 and 1. And this is going to be 1 or 0 and probably between 0 and 1. This is going to be basically normalized log probabilities. So those are all going to be between 0 and 1. And this is going to also be between 0 and 1. And so you already basically have this sort of equivalence between them inside of the loss function. Certainly your like regularization term is coming out of weights that are initialized, probably plural initialization. So they're already going to be like fairly small values close to 0. So you end up with this like basically even trade-off between them. But you're right that like you could try to think of trade-offs between them that are like different and parameterize that, and you could like do a bunch of runs to see whether or not it actually made more sense to prioritize the value net or the policy net. But yeah, it's not an unreasonable idea. So
how do you know that your estimates of pi are going to be sufficiently good to actually have this training start actually happening?
Yeah, I mean, empirically it works. So I guess the question is like, what are the actual outputs that the policy net should give you?
Roughly, how deep your money translation research is? Are they always to infinite?
How
deep do they tend to be, I guess?
Yeah, so it's so much heuristic. So I guess certainly if you're like late in the game, it'll be like way less deep. I think that there are heuristics that you can build in that like might let you cut it off and take actions faster if you're actually in the like performance context. So I guess if you know that you're going to like have to take the action in some amount of time, you don't want to search the entire space. But you will already have like that like best possible action in front of you up to that point. And so I guess like you're just evaluating the value net at like different subtrees to like slightly update your probabilities. That said, like you're doing self-play, and like all of the points in the game are valuable to learn about. And so since you're learning inside of the training loop, running it to the end doesn't actually like cost you anything, since like you need to do the learning anyway. So it's not as if you're at test time where like you just want the answer quickly. You actually want to like sort of search out all of the possibilities and just learn about those possibilities as much as possible. So I don't think it's actually bad to like search the entire space, because you're also like only taking the maximum action at each step, so it's likely to actually follow those paths. So it's not unreasonable. Yeah.
Any ideas when these estimates will or won't be good?
Will? Oh, so I guess like when will this work or not work?
It works in AlphaGo.
Yeah, that's a fair question. So I guess
there's lots of reasons
there
why
are
it won't work in
a lot of really strong exclusions. Oh yeah, no, it would never work in StarCraft because you like don't have complete information onto the game state. It's not sequential, so you can't run a tree search.
Just a continuum branching factor.
Yeah, well, yes, and like time is continuous. Yeah, I mean, the number of steps is just absurd. And yeah, don't get clean information about like which actions to take. If you take actions simultaneously, like your opponent's going to be like, yeah. So and there are like signals other than just like winning or losing. Yeah, I expected there to be more. There's this self-play assumption that's pretty important as well. So, like there are a lot of contexts where you can run RL, but you don't have the full simulator for the game. Like I guess that's pretty important. I guess you can only do this if you can actively simulate the world, and that just doesn't exist for a lot of environments that we care about. People are creating robotic simulators and trying to do transfer learning. Yeah, all those contexts I think a lot work. And incomplete information is pretty damning. Yeah, if you don't know the state of the world, it's hard to input the state to a network. And you can input this incomplete state that figures it out. Like they do this in Dota. And it kind of works, so we'll see how long it goes. So they don't do it on CTS. It's like just using a network and hoping its policy is good enough.
If it were a different game where you had something like a hexagonal grid, how do you think you should represent your input? Just like pad zeros and make it.
I mean, you could just increase the dimensionality. Sorry, what does a hex look like in hierarchy?
Why couldn't you do hexagons?
Yeah, you can do hexagons. You can do hexagons. You can't just do that.
Yes. Why not? Can we super sample and approximate it using a grid? I mean, that's super inefficient, but.
Yeah, I guess that, so I haven't seen any examples of this. Certainly, like, having a filter in your convolution, which was like, 3 hexes, like, organized with one another, and like using that as your input, and then having like, another set of higher level filters, et cetera, would just replicate the locality structure and, the location variant structure of convolution. So that'd probably just work. You could also zero things out, like somebody said. That might also just work. I guess that'd be kind of awkward then. Do you have a particular game that you're trying to simulate?
Well, I mean, the ones that are really hexagonal.
You can go for any geometry. I don't know, like, pick your polygon.
Locus would be interesting.
Which one?
Locus. Because you also play like 6 stones. Like the pieces you have. So it's like a triangular.
Oh, the different shaped pieces.
Yeah, you have different shaped pieces. And you try not to run out of place.
Okay. Yeah, I think convolution would still be able to represent the board stage.
Yeah.
It's definitely independent of that. But yeah, taking the accents changes things more dramatically. Yeah, I haven't seen that before. So you might be the first to like create hexagonal convolutions. Yeah.
So that like Q term that you showed us, the like average of the ones below it, right?
Yeah, that's right.
I don't know how to play Go, but like that's kind of an assumption about the game, right? That like if this node kind of looks good, then like spend resources on it, right? Because like it could be that you make this move and then you have to make the one good move after it, and any other one would just blow it up, right?
Yeah, that's right.
Like I don't know.
So I guess the value net, and so I guess like one assumption is like that the value net is accurate, so that you can run the value net on the states under it and see if they work.
Yeah.
So there's this question of like the fragility of the state, or like whether there's something that's close by that's still pretty good. And if it's likely that some other action would be played, then in one of your runs of MTTS, it'll go down this like maximum route, but in another run, there'll be some like probability over your inputs, as well as like this unvisitedness to the like parts that you haven't seen yet, that will force you to go down different paths that are like close to good enough. And so there's this nice ability with this heuristic to only have your value net look at states that are like good, but also that are importantly different from the states you've seen prior.
Yeah.
So I guess that it does account for that.
Oh, that's cool. I didn't
Yeah. And I guess like it's all recursive, so everything ends up really nice. It's kind of elegant, I think. Hey, thanks guys for your attention. It's been great.